Another useful flip-flop is the D flip-flop, and it can be a positive edge triggered flip-flop or a negative edge triggered flip-flop. It has two inputs, D and clock, and the convention for the clock is similar to what we already seen. This triangle indicates that it's an edge triggered flip-flop, and this circle here indicates that it's a negative edge triggered flip-flop. We can think of a D flip-flop as a JK flip-flop with K equal to J bar, and that input is taken as D. This is a possible implementation of the D flip-flop. And if this is a positive edge triggered flip-flop, then so is this. If this is a negative edge triggered flip-flop, then so is this one. And keeping this equivalence in mind between the D flip-flop and the JK flip-flop, it is easy to figure out the transition table for the D flip-flop. Let us consider D equal to 0 first. What does that mean? That means J is 0 and K is 1, and that means after the active clock edge, Q is going to become equal to 0, and that is what it says over here. Similarly, if D is 1, then J is 1 and K is 0, and then after the active edge, Q is going to become equal to 1, and that is what it says over here. So if D is 0, Qn plus 1 is 0. If D is 1, Qn plus 1 is 1. And the same table is also valid for this negative edge triggered D flip-flop, except of course for the active edge, which is a negative transition now. Let us look at these waveforms now to understand the operation of a D flip-flop. This is our clock waveform, and the active edge is marked with an arrow. In this case, it's a positive edge. This is our D input, and let us see what happens as a result of this input. At T1, what do? We look at the D value just before this active edge, and we find that it is 0, and therefore the Q output just after T1 is going to be 0, and then of course it does not change until the next active edge arrives. So therefore Q is 0 throughout this interval. What happens at this point? At T2, we look at the input D just before T2, that is T2 minus, and we find that D is 1, and therefore just after T2 our Q is going to become equal to 1, and then it's not going to change again until T3, and so on. Let us look at these waveforms now for the negative edge triggered D flip-flop. Here is our clock. The active edge is now the negative clock edge. This is our D input, and at T1 we are going to look at D just before the edge, and we find that D is 0. So therefore our Q is going to be 0 after T1, and then it's going to stay equal to 0 throughout this interval. At T2, or rather T2 minus, we find that D is 1, and therefore our Q is going to become equal to 1 after T2, and then it's going to stay equal to 1 up to T3, and so on. Alright, let us summarize. The D flip-flop can be used to delay the data signal by one clock period. So this D is called the data input, and that's why it is denoted by D. And what is this delay that we are talking about? Let us compare this waveform and this waveform, and we see that this output is a delayed version of the input, and the delay is one clock period, and the same thing happens here as well. With J equal to D and K equal to D bar, we have either J equal to 0, K equal to 1, or J equal to 1, K equal to 0, and therefore the next Q is 0 in the first case and 1 in the second case. This we have already discussed. Instead of a JK flip-flop, an RS flip-flop can also be used to make up a D flip-flop, with S equal to D and R equal to D bar. Let us now look at a shift register which can be made up with D flip-flops. In this example we have 4 of them. The output of the first flip-flop is called Q1, the second Q2, then Q3 and then Q4. The clock is common to all of them and that is shown over here. This D input is applied to the first flip-flop. So this D is shown over here and that is connected to this D1. The output of the first flip-flop Q1 is connected as D2. Similarly, Q2 is connected as D3 and Q3 is connected as D4. And now let us see what happens as a result of these inputs. To begin with, we have Q1 equal to 0, Q2 equal to 0 and so on, and that is also indicated over here. So all Q values are 0, and now the first active edge comes along, this one, and let us see what happens. Remember, we have to look at the D input of each flip-flop just before the active edge. Now for this flip-flop, the D input is this D here, that waveform, and just before this active edge its value is 1. So therefore Q1 is going to change to 1 and then it's not going to change up to the next active edge. Alright, what about Q2? For this flip-flop, Q1 is the D input and therefore we should now look at the value of Q1 just before the active edge, and we find that it is 0. Therefore Q2 is going to remain 0 and again it's not going to change until the next active edge. And the same thing will happen to Q3 and Q4 as well. So this is what we have after the first active edge. Q1 has become 1, Q2, Q3, Q4 have remained equal to 0. And that's also indicated here, 1, 0, 0, 0. Alright. Now after the second active edge, what is Q1 going to do? We need to look at D just before that active edge. D is 1, so Q1 will be equal to 1 after T2 or after this active edge here. What about Q2? We now look at Q1 because that serves as the D input for the flip-flop here, and Q1 is 1 just before the active edge and therefore this Q2 is going to change to 1. And then of course it's not going to change until the next active edge. What about Q3? For Q3, Q2 serves as the D input which was 0 just before the active edge, so therefore Q3 will stay equal to 0 and similarly Q4 will stay equal to 0, like that. So now we have 1, 1, 0, 0. And we can proceed in this same manner and see what happens. And we're not going to go through each step now, but just look at the results. So this is after the next active edge. And so on. And we observe that each output is a delayed version of the previous output. So for example, Q3 is like this and Q4 looks exactly like Q3 except it has got delayed by 1 clock period. That is one observation that we make. And also this D flip-flop has synchronized the transitions with the active edges. For example, our D input was not synchronized with the clock. These changes were not at the same time as the clock edges, but because of this D flip-flop, the first D flip-flop, output Q1 has got now synchronized with the clock edges. So that is how a shift register works. And you can try out this simulation. The circuit file is available.